Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome back to this series of lecture on elements of solar energy conversion. We are here at lecture number 29. So, in the last class we have started looking at one of the major and mature solar conversion technology, which is based on photovoltaic. So, we have started looking at how the semiconductors can act as a photovoltaic material, how the carrier concentration of electron and hole can be altered by doping, and two major concepts came towards the end of the class. One is density of state and the other one is Fermi function. Okay. We will continue working on them and we will look at how they affect the carrier concentration. So, we have looked at that the Fermi function for a particular energy level is of this form. So, first thing we can look at here is that it is a function of temperature, okay, and the Fermi level is defined. So, basically Fermi level is that energy for which Fermi function is half, or the probability of finding an electron in that energy level is 50%. Okay. So, now if we look at the effect of this in terms of the band structure, let us look at that now. So, suppose we have this energy and Fermi function. If we plot that, okay, how will that change? Okay. So, for Fermi function, you know, it is a probability. So, it can vary between 0 and 1. So, these are two hard limits, let us say this is 1. So, these are two hard limits for probability. Now, at a particular energy, so let us say this is the band structure for a particular material, okay, and the Fermi level will be here, right, 50% occupancy probability. So, Fermi level will be just in between the conduction band and valence band. Okay. So, if we draw the corresponding line here, so at 0 Kelvin the Fermi or the probability will change between 0 and 1 abruptly. Okay. So, in between you will have equal probability, and here what you can write, when the Fermi function is half, that means here it is half between 0 and 1, and this is the Fermi level. So, this particular curve it is for 0 Kelvin when there is no excitation available. Okay. Now, we have seen that for, let me use another color, for the n type semiconductor, or before I go to that, let us first look at how this will change the Fermi distribution will change with temperature. So, at 0 K we see that these corners are sharp. Okay. So, it is kind of a step function. Now, with higher temperature what will happen? This thing will smear out. So, at higher temperature this thing will smear out, but still it will cross the line at Fe equal to half. Okay. So, this one is temperature greater than, so let us say temperature 1 which is greater than 0 Kelvin. Okay. Now, at another level, if temperature is even higher, then smearing will be higher. Okay. And that is, so this one is T2 which is greater than T1. So, with temperature the smearing will be higher, but the crossing over will always happen at F equal to half. Now, if we say that for n type semiconductor we have this Fermi level itself is shifted towards the conduction band. Okay. So, suppose the Fermi level itself is shifted to the conduction band for n type semiconductor. So, EF n is the modified Fermi level for n type semiconductor. Now, what will that mean? Let me increase that or extend that line, and that will mean that for that particular material which is a n type semiconductor, the crossover will happen at this point. Okay, because that is the Fermi level, it has to be Fe equal to half. So, at that particular temperature what will happen, your Fermi level of that material will be parallelly shifted and move upward. So, this is probability distribution which is also the Fermi function at temperature T2 and for n type semiconductor. Okay. So, what we see that Fermi level is shifted upwards in the energy scale, and here on the other hand, if we have for a p type semiconductor, then the Fermi level will shift downwards to the valence band, okay, because now the whole concentration will be higher. So, the same thing now you will have parallelly shifted okay. So, for this one I should use another color, yeah. So, I should be consistent with the color. So, let us say the color will be this. Okay. So, this one basically is the Fermi function for n type semiconductor, and this one, the lower one, is the Fermi function for p type semiconductor. Okay. So, that is how the probability distribution or the Fermi function will change. You have seen that for temperature it will be smeared, more and more smeared as you go up from the from absolute 0, and for the doping it will be shifted parallelly. The whole thing will be shifted parallelly. For n type semiconductor it will be shifted up, and for p type semiconductor it will be shifted downwards. Okay. So, few observations we can write. One is that for intrinsic semiconductor, that means no doping case, in that case EF always at the middle of the conduction band and valence band, okay, or the in the middle of the band gap. Now, for n type it is close to conduction band, and for p type it is close to valence band. Okay. And we have talked about this close to, right, but how close? That will depend on the level of doping. Okay. So, you can say that if this is conduction band and this is valence band, and EF the Fermi level is really close to the conduction band, that means it is high level of doping. Okay. And for low level of doping you will have closer to the conduction band, but not that close. This is low level of doping. Okay. So, that will give you the qualitative understanding how the Fermi function is affected by doping as well as with temperature. Okay. So, similarly for p type, how close the Fermi level will be to the valence band will depend on doping. Higher the doping, closer the Fermi level. Okay. And doping, by doping I mean introducing impurity element in the bulk lattice of the pure intrinsic semiconductor. Okay. Now, when we have both the density of state and Fermi function, okay, we can evaluate the concentration of each charge carrier. Okay. Electron and hole we can evaluate them, but before we evaluate, let us look at how the qualitatively, I mean it is important to grasp the qualitative concept first, and then you can always use quantitative formula to evaluate it exactly. Okay. So, for electron you can find it by multiplying the probability of finding an electron, which is given by the Fermi function, and the number of available state, okay, and you can integrate it to get the complete number. Okay. So, let me first write it and then I will explain why I have written it. Okay. So, first thing is that this is concentration of electrons, or rather free electrons, because it is not just the electrons, electrons in the conduction band which are able to carry electricity or charge. Okay. And this 0 or O, this stands for the equilibrium case. Okay. So, N naught means the equilibrium electron density or electron concentration. Equilibrium means no applied voltage or no light or any energy rather input. That is what we call equilibrium. Okay. Now, we see that what we are doing, this is the probability of finding an electron at energy level E, and this one is the density of state at energy level E. So, if you multiply them, that will give you at that particular energy level what is the concentration, right, probability of finding an electron and how many states are there, that will give you the concentration, and you are integrating it throughout the conduction band or throughout the energies which are corresponding to the conduction band. That means, conduction band edge energy is E c, and from there all the way upward to infinity. Okay, to infinity. Okay. So, that is how the total number of electrons that are available in the conduction band at equilibrium is expressed in this form. Okay. And similarly, for holes you can write P naught, P stands for hole every time and N stands for electron. Now, P naught, again naught is for the equilibrium case. What you will have? Now, you will have to integrate it over the lowest level, which is minus infinity, to the valence band, to the top of the valence band edge. Okay. So, that is the integration limit. Now, for the probability of finding an hole will be probability of finding an 1 minus the probability of finding an electron, right. Either it will be a hole or will be an electron. So, probability of finding an electron will be 1 minus the Fermi function. Okay. So, that is the tricky difference that you have to note. It is not the Fermi function itself, but 1 minus that into the density of state in the valence band. Okay. So, by similar logic you will be able to find it. Now, qualitatively, if you look at how these integrating or integrations will give you the quantity, qualitatively, what you can draw, that if you have the conduction band, valence band, and this is intrinsic semiconductor. Okay. So, that means the Fermi level will be, let me continue this. So, this will be the Fermi level, and let me continue this one as well. Okay. Now, here we can plot three things. One is the density of state, okay, which we have seen that it will be somewhat like this. In the band gap there will be no density of state, 0, and as you go up in the conduction band, density of state will be increased, and as you go down in the valence band, the density of state will increase and it will follow a square root law, right. So, this we have seen, this is the density of state. Now, other thing that is important here is the Fermi function. Okay. So, we have seen that for a particular temperature, if this is 1, okay, for a particular temperature it will be somewhat like this, right. And so, this is the Fermi function. Now, what we are doing by integrating, we are multiplying these two and then summing up. Integration means summing up, right. So, ultimately for the electron density or electron concentration in the conduction band and the whole concentration in the valence band will be somewhat like this. Okay. So, this is N naught, which is for the conduction band, and this is P naught for the valence band. So, N naught, how we are getting it? We are getting it by this GCE FE and then integrating it. Okay. So, at any value, so this N naught will be basically the area under this curve and P naught will be area under this curve. Okay. So, any value will be GCE into FE for the conduction band, and for the other one, for the valence band, what we have is GVE into 1 minus FE. Okay. And for intrinsic semiconductor, you can see both of them will be same. So, this is the carrier concentration in conduction band and in valence band. Okay. Now, how these things will change if you dope, that becomes very interesting. Now, let us look at doped semiconductor. First, we will look at N type. N type means there are more number of electrons than holes. Okay. Now, N type also means that the Fermi level has shifted towards the conduction band. Okay. So, let us do the same exercise here. So, if we have EC, EV, okay, and now we have Fermi level which is closer to the conduction band edge. Okay. Now, let me extend these lines. Okay. Then do the same exercise here. Here we will have the density of state, okay, and it will be the same. Density of state is unaffected by the shifting of the Fermi level. Okay. Only the Fermi function is getting affected, not the density of state. So, density of state just stays the same as we have seen for the intrinsic semiconductor. Okay. But the Fermi level will not stay the same. What will happen? It will now cross over. So, if this is 1, okay. So, it will cross over the whole thing in the Fermi level. Okay. So, of course, the whole thing will be shifted, that means there will be lot of intersection in the valence band and there will be little intersection in the conduction band. Okay. So, this one is Fermi Fermi level or Fermi function for doped semiconductor, okay, which is shifted upwards. Okay. Now, what will be the effect? So, here you see that in the valence band the overlap is more, conduction band overlap increased because it is shifted upwards, right. So, this is valence band. Valence band the overlap is less, overlap decreased. Now, what will be the effect of both of these changes into the carrier concentration? Okay. Because the overlap increased here, you will have a thicker bulb at the conduction band and a very tiny bulb here at the valence band. So, this thing is the N naught for equilibrium condition, what is the electron concentration in the conduction band, and this is the P naught, which is the hole concentration. Okay. So, because of the shift of the Fermi level upwards, what you are getting? You are getting more overlap in the conduction band, and that is why the electron concentration will be higher there, and at the cost of the hole concentration. Hole concentration, because the Fermi level has shifted upwards, you have less amount of overlap in the conduction valence band, and that is why the hole concentration is lower. So, what we see here that N naught is significantly higher than P naught, which means electrons are the major charge carrier for N type semiconductors, is not it? Now, what happens for the P type? Just the opposite, of course. For P type semiconductor, what we have? We have again conduction band, valence band, and now the Fermi level is shifted towards valence band. It is close to the valence band, right. Now, again let me do the same exercise. So, first thing, the density of state, okay, and again it will stay unaffected. Then the Fermi function. Now, the overlap will be very thin here. Let me use another color. Overlap will be very thin here, while the valence band overlap will be much thicker. Okay. So, thicker overlap here in the valence band and thinner overlap in conduction band. Okay. Now, if you find out the carrier concentration, it will be just the opposite. You will have a small bulb here at the cost of a larger or thicker bulb here. Okay. So, here P naught will be much more than N naught, is not it? You see that this is happening only because the Fermi function is getting shifted downwards for the P type semiconductor, and the density of state, the G stays exactly the same. So, here P naught is higher than N naught, and that is how the P type semiconductor has holes as the dominant, or the term that we use is major charge carrier. Okay. So, that is how the Fermi energy and density of state are playing roles in this carrier concentration. Now, what we can do, this is well and good in terms of qualitative concept, how it is getting affected we know, but now we need to have some quantitative estimate of this N naught, P naught, everything, right. So, for quantitative estimate we need to have more useful terms such as the band edge density of state. Okay. So, we can, so the density of state is often reduced to an effective density of states at the band edge. Okay. Edge is the most important thing, as you can see the majority everything is happening at the edge, that is the interesting part of the whole semiconductor structure, right. So, if we have that, so for the electrons the conduction band edge which is EC is important. Okay. So, we can have that. So, GE can often reduced to an effective density of state at the band edge EC, and we name it NC. Okay. That effective value we name it NC, and same at band edge EV, that means that is relevant for the holes, and we name it NV. Okay. So, it can be shown again, this derivation is beyond the scope of this syllabus. So, NC, this effective value you can write in terms of 2 over h square, no, not h bar square, but h square into 2 pi mn star multiplied by kT whole to the power 3 by 2. Okay. The meaning of every term you know, h is the Planck's constant, mn star is the effective mass of electron, and T is the temperature, and K is the Stephan constant. Okay. And similarly, NV we can write, of course, the expression will be same, only thing we have to use the effective mass of hole. So, this gives us what would be the effective value at the band edge. Okay. So, instead of doing the integration, what we can do, we can just multiply that effective value with this the effective density of state at the band edge. So, now if we find the equilibrium concentration of electrons, that will be NC, which represents the effective density of state multiplied by the Fermi function, and again the Fermi function will be at the edge. Okay. So, here you can write NC and Fermi function at that particular value will be EC minus EF divided by KT, right. So, you have just used the definition of Fermi function. Okay. And this you can simplify with this expression EC minus EF divided by KT with a negative sign in front. Okay. So, this is an approximation when, and it is valid when this EC minus EF is greater than kT. Okay. So, rather much greater than kT, and which is often true for moderate temperature. If you go for really high temperature, then of course, this approximation of 1 over 1 plus e to the power something is equal to e to the power minus of that something is not valid if that something is close to 1. Okay. So, if big number, when the EC minus EF is much greater than kT, then you have a valid approximation. Okay. So, basically from this what we get is N naught is Nc into e to the power minus EC minus EF divided by kT. Okay. Now, we have some quantitative estimate of the carrier concentration in the conduction band for electron. Okay. And similarly, we have the whole concentration, which will be Nv multiplied by E exponential minus Ef minus Ev divided by kT. Now, it is other way round, because the energy is increasing or rather decreasing as you go deeper into the valence band. Okay. So, please pay attention to that. Okay. So, what it shows, both the expressions of N naught and P naught, expressions of N naught and P naught shows that closer the Fermi level to EC or EV, the higher the carrier concentration, right, because exponential function, this is a negative exponential function. So, the exponent, if it goes bigger, the value becomes lower. So, the EF, closer it is to the conduction band, you have N naught maximum, and EF, closer it to the valence band, you have P naught maximum. Okay. That is how it goes. And this is the same observation we have seen when we have looked at qualitatively. So, qualitatively we have seen the same thing, right. So, both the conceptual, the schematic concept should be clear in your head, as well as you should know what is the quantitative estimate of that. Okay. Both quality and quantity are important. Okay. Now, we need to relate the extrinsic semiconductor carrier concentrations to that of the intrinsic counterpart. Okay. That will tell us, okay, so how far we moved by doping, by making it extrinsic semiconductor, how much carrier concentration we could tweak. So, that is important to quantify. So, EF for undoped or intrinsic semiconductor is designated, let's designate it designated by EI. Okay. I stands for intrinsic, and corresponding carrier concentrations are Ni and Pi. Okay. If that is the case, then we can write that Ni is nothing but Nc e to the power minus Ec minus Ei divided by Kt. So, we have done nothing. In case of Ef, we have written Ei, and in case of N naught, we have written Ni. Okay. So, basically from the extrinsic part, we have used the same expression, just for intrinsic we have named that Ef to be Ei. Okay. So, this is true as N naught tends to Ni as Ef tends to Ei, right. So, this expression we can write for intrinsic semiconductor, and for Pi what we can write Nv e to the power minus Ei minus Ev by Kt. The same thing again we have done. Ef we have replaced by Ei, and P naught we have replaced by Pi. Okay. Now, by simple algebra you can show that this N naught you can write as Ni e to the power Ef minus Ei by Kt. So, what we have done, from N naught and Ni expression we have eliminated Ec. So, we have eliminated Ec. So, we are left with Ef and Ei. Ef is the doped semiconductor Fermi level, and Ei is the undoped Fermi level undoped semiconductor Fermi level. And similarly, P naught will be Pi e to the power Ei minus Ef divided by Kt. Okay. So, here what we have done, we have eliminated Ev, right. So, that is giving us how the carrier concentration is changed as you dope, right, compared to its intrinsic value. So, note that the equilibrium carrier concentration are function of temperature, right. Everywhere we have this Kt thing, right. So, that means it is a function of temperature. So, it is not only because of this Kt, because of the exponential part, but also for the pre-exponential prefactor. That means Nc, Nv, the small ni, Pi, everything they are functions of temperature. Okay. So, that means it is a strong function of temperature, because both the exponential parts are anyway changing largely by a small change in temperature. They are more sensitive functions, and the pre-exponential thing also it has this temperature dependence. Okay. Now, another very important, I should stress it with maybe red stars, very important observation that you can see is, if you multiply these two carrier concentrations. One is electron carrier concentration and the whole concentration. If you multiply that, you will see that it will be same as the multiplication what you get for the intrinsic value. Okay. Because if we go back to the expression, here you can see that if you multiply n naught and p naught, then the exponential parts they are reciprocal to each other. So, they get cancelled out. Okay. So, what you are left with is n naught p naught is equal to n I p I. Okay. So, as the exponential parts cancel each other. Okay. And for NiPi we know that that is what? That is Ni squared, right, because for intrinsic semiconductor the number of electron and number of holes will be the same, right. So, Ni is equal to Pi, that means NiPi gives you Ni squared. So, that is a very important, very important observation you should make. Physically what it means is that the doping allows us to tweak the number of a particular carrier right at the cost of the other carrier. So, it is very important to note this at the cost of. So, if you want to increase the number of electrons in the conduction band, the cost is coming at the reduced number of holes in the valence band. So, their multiplication does not change. Ni is a material property, right. So, Ni you cannot change by doping, even by doping you cannot change it. So, if you cannot change Ni, that means the product of N naught and P naught you cannot change. So, if you increase N naught, P naught will has to decrease. So, one carrier is increased or the number is modified at the cost of the other carrier. Okay. So, when in N type semiconductor the N naught is increased, P naught automatically decreases to keep the product constant, as Ni square is invariant for the substrate semiconductor. Of course, here I should mention that if you do heavy doping, okay, then you cannot call it a substrate semiconductor anymore, because it will form a kind of an alloy. So, if you put lot of aluminum in silicon substrate, then it will form an silicon aluminum alloy or some intermetallic. So, you cannot just tell it to be a doped semiconductor. In that case, the material itself got changed. So, Ni will also change, then you can have this N naught P naught to be some other value, but that is never happens. In reality, you dope much smaller quantity than the substrate. So, now we are going to start or going to look at the motion of this carrier. So, ultimately when the carriers are in motion, then only you will get this photovoltaic effect, right. So, photovoltaic effect it is the result of this carrier motion If they do not move, then you do not have any current. So, just not the concentration, but the motion that is important. Okay. So, I will just start it today, and in the next class we are going to elaborate on this, but let us just start what do we mean by carrier motion. So, one thing is that we have seen the quantity of carriers, that means N and P, okay, under equilibrium condition, and that is why we call them N naught and P naught. Naught means equilibrium. Now, when this equilibrium is perturbed, then they will be set in motion, then they will move, isn't it? Under equilibrium nothing can move, there is no driving force for any carrier to move, but when you perturb the equilibrium, then the carrier motion will change, I mean the carrier will start to move. So, some force is needed for them to move. Okay. So, that can be either the sunlight which is causing increase in energy of individual carriers, and it can be the some voltage if you apply from outside, that will also perturb the equilibrium and that will set the carriers in motion. Okay. So, we will look at these different kinds of carrier motions in the next class. Thank you for your attention.